Okay, so homework C2, or the last homework was due. The new homework has been posted. It is technically due, I guess, on Tuesday, but for this special homework, you guys can use the availability date as the due date. There's going to be no late penalty, just to keep things consistent with the syllabus as much as I can. I still make it due when it was intended to be due, which was on Tuesday, but in order to give you a little extra time to work on it and get the solution set out before the midterm, then there's no late penalty that'll be applied to this. So you can go ahead and turn it in up until the normal Saturday availability window and don't have to worry about any of the discount. Those, if you haven't taken a look at it, there's two questions related to random variate generation. So the C homework was random number generation. Random numbers we define as a random, uniformly distributed random variables between 0 and 1. That's, we shorten that to say random number. A random variate is more general than that. So there's two questions for that. There you can expect to see random variate generation as kind of the most advanced thing on the midterm. It's kind of like where the midterm will stop. So this homework kind of can double as exam practice. A couple of little tips that I might mention is that the hiccup that a lot of people have here is they say, well, I remember how to take antiderivatives, but these definite integrals seem to trip people up. And so you have to remember that when you're integrating something piecewise, as most of these CDFs or these PDFs are, then you have to kind of integrate each piece separately, but then add in the component from the previous piece. And so a CDF is integrated from -infinity to x. But if that CDF crosses two pieces, one piece that was from -infinity to 0, and another piece that's from 0 to whatever x you're looking at, then you have to take the integral from -infinity to 0, which is just going to be a constant. You've got to take that first before you take this part here. And this part here, a lot of times students will just do this part and forget about the parts before it. So you have to break these intervals up and make sure you really are getting everything from all the previous intervals. And I have some sample problems that I've done online associated with this on Canvas associated with this homework you can take a look at if you want to see examples of that. The other thing is that, and I usually put on this homework assignment something that kind of exercises this demon, is that if you have a CDF that has a squared in it, when you generate the inverse, when you do the inverse transform to get the random variate generator, you're going to end up having to take a square root somewhere because that effectively inverts this relationship. But if you invert a square, there are two relationships you could get out, the positive square root or the negative square root. And which one you pick will depend upon the intended range of your random variable. So if you're looking at a random variable that is negative in this region, then you should probably make sure to choose the negative one. Now, when I say choose the negative one, it could be the expression here needs to be negative, and that might mean choosing the positive one in order to make the expression corresponding to that piece negative. So you just have to be careful that the region of the range that you're solving for matches to your choice of this when you take this guy here. So those are kind of the two tips. This is kind of the problem 1 tip. This is kind of the problem 2 tip. You will be asked to generate a histogram using whatever program you'd like, let's say Excel, of the random variate generator that you end up generating. So you're actually going to be able to generate this. And so you will have, thousands of rows in a spreadsheet or something like that. And we don't just want you to copy and paste those thousands of rows into a Word doc. And so your submission should be readable. And so I'm looking for the histogram. I'm not looking for the rows of numbers. And so it's great to show your work to sort of include any Excel spreadsheet that you used as an auxiliary document. But the main bulk of your document, so like where the main results are, including that histogram, should be in the main document, that docx or that PDF file that has that in it. And the other thing I might mention is that another thing that sometimes people get tripped up in is sometimes they accidentally will histogram the random numbers that go into the random variate generator and not the outputs of the random variate generator. So if you're not careful, you end up just getting a uniform distribution out in your histogram and that's not what we're looking for. So make sure you do that. In all of your histograms, make sure you're engineers. So we care about units, we care about titles, we care about axes labels, and so on. And so make sure you've got a title on the top, a descriptive axis label, proper axis scaling as well. And so make your plots useful. We love plots as engineers. I had a probably an inappropriate electromagnetics instructor in undergraduate who said something like it's instinctual, it's vital, it's like sex, engineers got a plot, or something like that. And it was very memorable to me, and that's why I'm telling it to you. Not necessarily the words I would choose, but it is very much like whenever you see data, you for the rest of your life are going to communicate in plots. And so start now, make sure they're good looking plots. The ICAF, this is a long ICA. Instead of being worth 10 points, it's worth like 35 points. And you can take it as many times as you want. It samples from all the previous ICAs. So every time you take it, you might get slightly different questions than the last time you took it. It will take the highest score. So if you take this ICA, it doubles as midterm studying prep, but it also gives you those points. I also took the midterm from last year, and I stripped out a couple of administrative questions at the top and turned it into a practice exam. So you can take it, it'll give you a score, but that score doesn't go anywhere. In fact, I don't think I even see that score. So that is in the unit F2, the midterm unit, that you can end up taking, and it's another way to have interactive practice preparing for the midterm. So lots of other helpful resources on Canvas. Sample midterms, I think I've got sample midterms going back, I don't know, at least 6 years. Lots of stuff on there. In order to unlock that, you've got to do the Respondus compliance check, which is in that unit F1. It'll take you 10 minutes at most, 5 minutes probably. It's just to guarantee that you and your computer have the ability to take the exam. This does, because for those of you that are in a classroom right now, for people who want to come to the classroom during stage 1 where the Respondus is up. So I've said for technical challenges, instead of making a 75-minute exam, I've provided 90 minutes, even though I've designed it to be completed within 75. But then so that creates kind of a logistical challenge for the classroom, because you guys really can only be in here for 75 minutes. So if you want to take the exam in the classroom, then the only option I really have for you is that you've got to submit your exam before you leave, because I couldn't have you leaving for 15 minutes, with the Respondus running as you're like walking around to the laptop or whatever. So if you come here to take the exam, again, the exam's been designed to be, for most people, to finish it within 20 to 30 minutes. A couple people will, probably take, the bell curve is really designed so that, it's like a Six Sigma thing. I want to kind of make everybody feel like they have plenty of time in 75 minutes. Only reason I've allocated 90 is just for technical challenges. So if you're home, something weird happens, you can't quite get Respondus up and running, provided a little bit of extra time. So if you want to come here to do it and have me live proctor, then that is fine. But I have to ask everybody before they leave to make sure they submit their exam, so that we don't get some weird collaboration, these sort of things that can go on, like closing your laptop, going outside, talking to people, opening your laptop back up, reconnecting to Respondus, and then trying to quickly fill in some questions. I don't want any of that sort of stuff to happen. So that's why I've got to ask you to submit before you leave. Okay, any questions about exam stuff coming up? I also check online, but I'm watching in person here. So the question online was, if you come to the classroom, will locked-in still be used? Yes, it was the simplest thing. Rather than trying to create a code because then I have to worry about who has access to the code. I'm just going to make it simple. And if you come to the classroom, we'll still use lockdown. But when you scan your environment, I'll see you're in the classroom. You can even like show me when you scan your environment. And then that way, when I review everyone's, it'll be fine. Like, oh, that's, they got people around them, but that's not a big deal. They were in the classroom. So if this was a different type of proctoring environment, then we could probably do it without Respondus, but do the complexities of things, still Respondus in the classroom. I could have also given a paper-based exam, but I wanted to have the grading done in a consistent way and not have to worry about grading some and have the others auto-graded. Any other questions about the exam stuff? Yeah, and so the comment online was that I know it gets tricky. Sometimes it picks up other people around. And again, I'm the one who ultimately reviews all the videos. So I know what's going on, and I don't trust Respondus's like auto classification stuff. So don't worry about like, you know, a dog barking or a person sitting next to you in the classroom or whatever. Like, you know, if I'll end up taking a look and use common sense. Okay. From labs, they're Arena now, so make sure you have access to that lab textbook, which is online. I think pretty much covered things there. Great. All right, so before we get to today's stuff, so last time I didn't get to the discrete distributions, and I definitely want to make sure that we cover these, because these are things that we can imagine you'd see on an exam too. So we covered before the kind of common continuous distributions that you'll use when doing input modeling. So I've got this type of process in my system. What type of distribution might I expect? Oh, that's an exponential, that's a normal, et cetera. So what about discrete stuff? And so there are times where we need to model discrete random variables inside our simulations. And so the kind of common discrete ones are these 5, which I'll go through kind of quickly, or these 4, which I'll go through kind of quickly. So I mentioned that so far 3 exponential related continuous distributions: the exponential, the Erlang. Can somebody tell me what, roughly speaking, like in a couple of words, how does the Erlang relate to the exponential? On line 2. So if I said I had an Erlang 3 distribution, what does an Erlang 3 distribution represent? Using, yeah, the sum of 3 exponentials, right? So an exponential is some distribution. You know, it's got exponential could be here, 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 whatever, but you know, it's described by the exponential curve. If you add up 3 independent exponentials, you get a distribution that looks a little bit more hump shaped. And what does that distribution? That's the Erlang 3. So the Erlang was one. Then the Weibull was like an exponential where they added a little shaped parameter for convenience, so they could stretch the exponential to have it a heavier tail, or maybe they can make it more humpy, those sorts of things. And so that shape parameter in the exponential added, that's the Weibull distribution. So any of you who go into reliability engineering, guarantee you'll see Weibull plots. You'll hear about, you know, this thing's got, this is modeled as a Weibull distribution with a certain parameter. So those are 3 exponential base. They're all sort of like the ideal is the exponential, but then when there's a sum, it's an Erlang. When it needs to be stretched a little bit, it's a Weibull. The discrete extension, one discrete extension of the exponential is the Poisson. Now, we're going to talk about Poisson processes, but this is the Poisson random variable. A Poisson random variable is a discrete random variable. Because there's a Poisson process related to this, people often get confused, and sometimes I think they confuse exponential for Poisson. The Poisson, it describes the number of exponentially distributed events that occur in an interval. So if we were to say, I know that for a certain hour, people arrive to the airport, maybe 1 per minute, then I could say on average, I get 60 arrivals per hour. Well, I say, well, what's the actual distribution of arrivals you get in any given hour? Well, that is what you get here. So it's a count of arrivals. So given that I know how often things arrive within an interval, and I know the length of that interval, then what's the distribution of the count of things that happen during that interval? And that is a Poisson random variable. And so, you know, it has, this is its probability mass function. They connected the dots here. I think I borrowed this graph maybe from Wikipedia. I would never connect the dots in a PMS. Because it doesn't make any sense. You're not interpolating, but these just should be just dots, or dots with those little hairpins on them. But so don't think of this as a continuous distribution. This is a discrete probability mass function for the number of things that happen in an interval, given that you know the rate at which they arrive during that interval. And this is its CDF. Interesting features about the Poisson: the mean and variance are equal. So it's a 1 parameter distribution. And that parameter alpha, if we want to relate it to the exponential, remember the exponential's parameter is lambda. It's the rate of arrivals. Alpha can be viewed as that lambda rate times the length of the interval. So I said before, if we had an hour and we know that you get 1 arrival per minute, then we'd get 60 arrivals per hour. Well, right there, 60 arrivals per hour times 1 hour, that tells me that my alpha would be equal to 60 right here, because that's 60 times 1. So this alpha, again, you can think of as lambda times interval length. And that's how you get a connection between the exponential and the Poisson. All right, questions there about the distinction between the discrete Poisson and the continuous exponential? Okay, questions online? So I'm just driving home. Poisson is discrete. So there's a question on the midterm about like, try to name a distribution that is discrete or whatever. Like, you know that Poisson should be one of the ones you're considering, and exponential you should cross out because I said discrete, so you can exclude it. Okay, now there are a couple of distributions I want to make sure we know that are not based on the exponential. They're based on a Bernoulli trial, and so a coin flip. So many of these distributions in the continuous space, like I said, were sort of derivatives or derived from the exponential. There's another kind of framework we can think about, and it's in terms of successes and failures or coin flips. And so if I refer to a Bernoulli trial, that is a fancy way of me saying a weighted coin flip. So a Bernoulli trial is just a random variable that comes up 1 with probability p and 0 with probability 1 minus p. So that's the probability mass function here. And so the mean value of a Bernoulli trial is the probability, and the variance is this thing that I'm not going to dwell too much on, but later on when we talk about confidence intervals on quantiles, we'll see this quantity come up, and it comes directly from this. So this p times 1 minus p. And so this just models a single outcome. So that it by itself isn't anything that exciting. But what we do is we take the Bernoulli distribution, which is this just weighted coin toss, and then we can ask questions about how many successes and failures under which conditions and so on and so forth. So a binomial distribution, which I denote by using B and then N for number of trials and P for probability of success on each trial. This here is the number of the count of successes that I would get in a number of trials. And so so if I'm looking at the probabilities here, so if my probability is 0.5 and my number of trials is 20, those are the blue dots. So the blue dots, which point out here to those online, this peak here, then we can see that there's a certain distribution that is peaked, or its mode is at 10. So that kind of makes sense that if I flip a coin 20 times, I would expect the mean, on average, me to get 10 heads and 10 tails. But in reality, it's actually really rare to get exactly 10 heads and 10 tails with a fair coin. Sometimes you're going to get less than that. Sometimes you're going to get more than that. It's very rare to get 20 heads. That's why the probability is like 0 down here, to get 20 all heads or 0 all heads. But it is not uncommon to get some mixture of these. And so as the N gets lower and lower, then like if you flip a coin 5 times, regardless of what the probability is, you can get a really wide range of outcomes. So this is part of the reason why if you're playing a series like a basketball or sort of any sport that bases a tournament off of 7 games, then if we think about 7 games in terms of a binomial distribution, ideally what you'd like in a tournament is effectively to do a hypothesis test of saying, is the probability different than 50%? Are these teams different, and which one is better? But it turns out that if I were to make this N equal to 7, there's absolutely no way that I can tell that. So there's no way from a purely binomial perspective that in having only 7 data points, that they can discriminate between really any probability, whether it's 0.3 or 0.7 or whatever. So I can't really tell which team is better unless they start playing more than 7 games. But nobody want to watch like more than 7 baseball games, right? Like that would just be really boring. So nobody does that because you can't sell commercials for that. So you're effectively, you sell 7 baseball games, you're selling coin flips because the outcome may as well be random. And so that's kind of what's being captured here in the variance here. So a binomial distribution is the number of successes you get when you have n trials, like in games, with a probability p successes, where if we're thinking in the sports analogy, the probability p can be the probability that one team beats the other team, for example. All right, does that make sense? The binomial distribution, how it's a build up of the Bernoulli. Now, there are other questions we can ask about weighted coin flips, like not how many successes do we get in a certain amount of trials. We can ask, okay, that's me just summarizing this. I can ask a slightly different question. I'd say, how many trials do I need in order to get a certain number of successes over that whole, not a string of successes, but just over all of those trials? How many trials do I need to get a certain number of successes? And that's the negative binomial distribution. And so the number of independent Bernoulli trials until the rth success. And so the negative binomial has got R and P. So it doesn't have an N anymore. It has R is my desired number of successes, P is my probability of successes, and it is the distribution that I get out. So whereas the binomial distribution, it's never going to be supported higher than its n. So because you don't do more than n trials. In the negative binomial, which I don't have a graph of, in the negative binomial, this could be supported all the way to infinity, because we don't, in theory, you need an unbounded number of trials in order to get enough successes, as R successes. So that's what we mean by, so it's like, how many times do I need to, this is like the Russian roulette kind of problem, is that given that you have a certain probability of a failure, so how many times do I need to run a machine that has a failure probability of 10% until the machine breaks down? And so it could happen on the first time, it could happen on the 100th time, but I want a distribution of those things. So how many do I need to go until I'm going to get my first failure? And that's what is modeled here. There is a special version of that called the geometric distribution, where R is equal to 1. So when I set R equal to 1, then this is the number of trials until the first success or the first failure, whatever our semantics are on this probability. So that geometric distribution is the analog of the exponential. So the exponential is the time until an event, where we have this memoryless property and all that sort of thing. You can think of the geometric as the discrete time until an event. How many clicks of the clock do I get until a certain event happens, given that the certain event has a certain probability of happening at every click of the clock? So maybe this is more the Russian roulette problem, because once you get the failure, that's the end of the game. Okay. So questions about the negative binomial or the geometric? Counts of well, in this case, counts of trials until certain criteria are met. Okay. All right, so the last thing that I want to make sure that we cover is all of these things so far have been what we call random variables. There's another concept we need, which is the random process. A random process is what we call an index family of random variables. So it's a collection of random variables that all have some index, like time, that relates one random variable to another. So for example, a counting process is a family which we would index by t, where t is time, and time could be anything greater than 0, so it could be continuous, where at any time, we have a random variable, which is, say, the count of events up to that time. So a counting process is like if we were to say how many people have arrived at the airport. Well, at time 0, there's some distribution. At time 1, there's some distribution. At time 2, there's some distribution. All of that together becomes a counting process modeling the whole arrival stream to the airport. So it's a collection of random variables. And in this class and in classes like 470, you'll focus on the Poisson counting process, or just shortened to the Poisson process. The Poisson process is a special counting process where there's no simultaneous arrivals. They occur with probability 0. There's what they call stationary increments. And what stationary increments means is that the distribution of arrivals between any two times only depends on the difference between them. So if I want to say like how many people arrived in the first hour and how many people arrived in the second hour, all I need to know is that it's an hour-long duration that I'm asking about. It doesn't matter that it's the first hour or the second hour. That's what we mean by stationary increments. Now, there are, of course, at an airport, that's not going to be the case, is that you're going to have a different arrival process for the 9 a.m. hour as you are for the noon hour, and so on. And so in that case, what we'll do is we approximate this violation of the stationary increments process by basically thinking about different Poisson processes that flip. You do one Poisson process in 1 hour, another Poisson process another hour, and so on. And that idea of a Poisson process whose rate changes over time is something that we're going to call an inhomogeneous Poisson process. So this is what we call technically a homogeneous Poisson process, which means it's got these stationary increments, but there are inhomogeneous. And when in lab, you're going to build Poisson processes in ARENA where you schedule the arrival rate so that at different hours, you can have different rates. So that's possible to do in ARENA. It's pretty easy to do. And then independent increments, which is just saying that if you have two non-overlapping time intervals, the variance, the distribution of those two time intervals will be independent of each other. So if you know that we got slightly more than average arrivals in the first hour, then in the third hour, which is not overlapping, we can't say anything about whether we're going to have slightly more than average or less than average. So those two distributions are independent from each other. All right, so that's what we mean by Poisson process. Any questions about this idea of a process or a counting process or this counting process with these assumptions? Again, something that if you haven't taken 470 yet, you'll see all this again in 470. Okay. All right, so we say, how does the Poisson process relate to all of the random variables that we've talked about so far? Well, I can give you a Poisson process with a rate or intensity lambda. So I'd say I've got a Poisson process with rate 5 people per second or 5 people per minute. And what that tells me is that the probability of the number of arrivals up to time t has this distribution with this lambda. In other words, nt is Poisson distributed. It's a discrete random variable where its parameter is the intensity parameter times t. So this is what I was telling you earlier, is that t you can think of as an interval from 0 all the way up to t, and in t, which is sort of, the kind of the bulk of the Poisson counting process, it's distributed like a Poisson random variable where its parameter is lambda times that interval length, lambda t. And I heard something online. Was there a question? I think somebody went off mute. All right, thanks. Okay. All right. Yeah, so that's where it gets its name. Now, if I look at the time between arrivals, so if I've got two adjacent arrivals, so arrival 1, arrival 2, the time between the arrivals is distributed as an exponential with rate lambda. And this goes back to me saying before, like, how does a Poisson relate to an exponential? Poisson is the count of exponentially distributed interarrivals in an interval, and that's all that we're saying here. So we usually associate with a Poisson discrete random variable for the number of things that happen in an interval, and we associate with the Poisson an exponential for how spread out each one of those things that happens is. And so that lambda tells us enough to get both of these distributions, the lambda and the t together. So if you have both of these things, Poisson distributed counts and exponential distributed interarrivals, that is necessary and sufficient to say you have a Poisson process. So the two things are just equivalent to each other. All right, so any questions about these definitions? So when I say that's what we mean, I got a lot of information when I tell you it's a Poisson process with rate 5 people per minute. You immediately know these things, this random variable for that, this random variable for that. Okay. All right, so, and then this is what I mentioned before, inhomogeneous or non-homogeneous Poisson processes, sometimes called NHPPs, they have a time varying rate, and we can approximate that by scheduling an arena, and you will see that in lab 6, which is coming up pretty soon. So, oh, and about the labs, give a second to stare at this slide. So I was a little confused because the physical labs had 16.1 on them, so I assume the virtual labs also had 16.1 on them. Turns out the virtual labs currently have 16.0, but I got an email last night saying that they're in the process of upgrading the virtual labs to 16.1. So soon, all of the labs, virtual and physical, should have 16.1 on it, and it'll be pretty safe for you to have 16.1 on your computers. The only thing that will be unsafe is if you open a model or you create a model in 16.1, if you then take it to a computer with 16.0, you won't be able to open that model. The other way works fine. So if it's a 16.0 model is created there, you can then open it in 16.1, that's fine. But hopefully everybody will be on 16.1 soon, and we'll be at the state of the art. All right, so any questions about this, these definitions? I think I've just got a bunch of properties here, but I'm pretty much gonna, this is kind of was just bonus and kind of icing on the cake. And so we don't do a lot of queuing theory in this class, but again, in a class like 470, you would. Once you know something is a Poisson process, there's all sorts of really cool stuff you can do. And that if I was more pedantic, I could ask about on a midterm or a final exam. So like, if you have a Poisson process coming into a branch and you just randomly decide these people, some people are going to go one way, some people are going to go another way. The two processes you generate through the splitting also are going to be Poisson processes, but they'll have a rate, which is going to be the original rate times the probability of that branch. Like there's all sorts of really cool stuff you can do where if you start with a Poisson process and you have a diagram of a queuing network, like again, you'll see in 470, you can just push that thing through that and it just gets split up and put back together and it's just Poisson all over the place. So it's a wonderful property because it ends up being an invariant property for these queuing networks. And it turns out a lot of systems, if you focus on a narrow enough time, can be approximated by Poisson processes. Once you go to kind of large amounts of time, it gets a little stickier and you need to do things like you will experiment with in lab 6. So I think that's all I wanted to cover from that we missed last time before we move on to random number generation today. So any other questions about just our basic probabilistic models that I want to make sure that you have some comfort with by the end of the semester as your kind of entry into stochastic modeling. These are the tools in which you assign to inputs in stochastic modeling. See a question online. There's a question that I'm not completely, it says for the snapshots required in the lab, do you want them to be run after the simulations have been run? Oh, I see. So like when you're taking I think the question is about actually taking the models. So I'm okay with you. I think unless we're adding, so eventually in one of the future labs, you'll add a visualization or you'll add visualization components like graphs and things to the plots. And when you do that, then I will want you to sort of populate or, show me a shot of the sim after all those graphs have been populated. But for most of our labs, there's hardly any difference between what they look like before and after. I mean, when it's after, you just see maybe numbers. So I don't think Shin is going to notice either way. So, and I'm not going to make a hard requirement. I think just show me that show me the model that you've drawn and show me whatever outputs stats that we ask you for. So unless it explicitly says otherwise, I don't really care if the screenshot is before or after the model's run. Any other questions online? Great. Okay, all right, well then let's get into something a little more colorful and less text heavy. All right, so yeah, so we've been got a lot about probabilistic models now, and each one of those probabilistic models maps to an input. The input is squeezed through our process diagram that we've drawn in ARENA, and we get variations on the output. And so we've learned a bunch of these that we just talked about here, continuous discrete processes. And so once we choose the distribution, we have to simulate, we have to actually get the computer to generate those things. So how do we do that? How do we sample? That's the term we're going to use. How do we sample from a desired distribution? And so, you know, if we have a model, for example, the lifetime of a device that inspects cracks in an aircraft wing, in our simulation of the whole process of how this manufacturing process is going or whatever, we need to accurately know when this machine dies. So we need to simulate realistic failure times that we say are exponentially distributed. Well, how the heck do we get exponentially distributed failure times out of our simulation? And so if we start with an exponential, we've got the exponential's PDF like this. If I take the integral under the PDF, I get all of that area as it accumulates as the CDF, which I can plot like that. So I've now got a CDF of the exponential, and that CDF of the exponential happens to go from 0 to 1. It always goes from 0 to 1. That's the property of CDFs. So it's always been possible to then take a uniformly distributed random number. So you have a random number generator, generates numbers between 0 and 1. And those are, you know, uniformly spaced across 0 to 1. There's no, it's not like the numbers near 1 are more frequent than the numbers near 0. It's uniformly distributed, could be anywhere along there. And if I invert this CDF, as we'll talk about doing next lecture, as you'll have practice in doing in the homework, then I then can turn those uniformly distributed random numbers into exponentially distributed random variates out here. And so you can see here that because this is shaped like this with this kind of hump, then numbers that are generated between say 0 and 0.5 tend to clump. And that's why you get an accumulation of numbers at these lower values. But then numbers that are generated up here, say between 0.5 and 1, get spread out. And that's why you get this kind of longer tail over here, which is what we see there. So that's the inverse transform technique. So in theory, as long as we have a CDF and one of these, a uniformly distributed random number generator, which you could think of like the computer version of a 20-sided die, we can do this for anything. But then that then suggests the question, how the heck do we get that? How do we generate that to begin with? These are deterministic machines. They are not fundamentally random. How do we get that number there? They're good at math. So ideally, we need to create mathematical expressions that can be run on that machine that will generate numbers between 0 and 1 uniformly. Now, von Neumann, who's one of the ones who came up with the architecture for these machines, had this nice quote: anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. I like that quote because one of the first methods for generating random numbers arithmetically was actually pioneered by Franciscan friars. So I guess there's always been a close relationship with sin and random numbers generation, at least from math. Now, so how did people, have people done it back when computers were a little slower? Well, this is in part a little bit of a joke, but this is realistic. There, you can go to Amazon and you can search for a small book of random numbers, and there's this book for 15 bucks, and it has this quote: creative people who like to make use of chance in their work will find this convenient source, a convenient source of random numbers. What's inside it? You can look inside the book, and here's some previews. So these are what pages of this book look like. So just rows and rows of random numbers that you can then reformat however you'd like. You can put decimal points, whatever you want, and all that. And so if you need another random number, you just go to the next row of this book and you get the next random number in your application. So in principle, you could use a book to generate these random numbers. And once upon a time, this actually was closer to what people did when they needed to generate random numbers. If you're randomizing an experiment and you wanted to figure out which participant goes next and say a sequence or whatever, then people would flip to random number text like this and say, all right, looks like participant 7 is next, and so on. So this is not totally a joke. But modern times we have computers that do this for us. So you go into Excel and you've got functions like rand and rand between. You go into MATLAB, and if I type rand and let it autocomplete, there's a whole bunch of random number generation inside MATLAB. But the question is, where do these numbers come from, and are they reliable? So what does it mean to even assess the reliability of a random number generator? Well, can somebody tell me, if I had a 20-sided die, what are some things that you think would be good about a good 20-sided die? For playing a game that I need a 20-sided die, what are some properties that you would expect of any good 20-sided die? Anybody? Yeah. Equal probability of landing on any number. I would say that, yeah, that's great. That's what I would call uniformity. It's uniformly probable that it's going to land on any number. So that is definitely something I want here. When I pick up that die, I don't want it to be biased towards 20 or 1. I want it to be anything. That's kind of like one of the properties. Is there anything else you can think of that I might want when I have this 20-sided die? The second property that I'm looking for is a little more nuanced. So when you roll the die, when one person rolls a die, I'm going to see online if anybody's got anything. If one person rolls a die, you hand it to the next person. How do you want those two rolls to relate to each other? So I roll a die, I get a 15. I hand it to you. What's the relationship between my die roll and your die roll? What was that? Independent, right? They should be independent of each other. That's the other thing I'm looking for. So I want to make sure that every die roll is kind of each individual die roll is uniformly distributed between 1 and 20. And if I know information about the previous die roll, it doesn't change the distribution of the next die roll. So every die roll is always uniformly distributed between 1 and 20, regardless of what information I have about the previous die rolls. And so that is effectively uniformity and independence. And that's what I need to build in my pseudo-random number generator, my mathematical expression that's implemented inside the computer. And and I got independent online as well. So thank you for that. So what do we mean by uniformity? So for each, and again, so random numbers, that is my shortened name in the book shortened name for uniformly distributed random variables between 0 and 1. We call those random numbers. So each random number should have the property that the density across all outcomes is equal to 1. So it's a continuous random variable. The density is equal to 1. And the expectation is equal to 0.5. So it's kind of balanced right there in the middle. If I want to operationalize, like, how do I assess that? One way I could say that is if 0 to 1 is divided up into little n subintervals of equal length. So I cut this thing up like a chocolate bar or something like that in equal size pieces. The expected number of random numbers in each interval should be equal, and it should all be the number of total random numbers I've drawn divided by the number of subintervals. So that is this is sort of a prediction that we're going to make use of when we test for this. So like we were saying with the 20-sided die, they're a good roll of a 20-sided die, or a good 20-sided die produces a string of outcomes that looks like this, where there are some repeats, but I don't see a preponderance of lingering around certain numbers. A bad die roll might be like one of these ones, whereas I've highlighted, you see a whole lot of 2s, a whole lot of 7s, a couple of 1s, but you don't really see a whole lot of the numbers in between. So this is what I mean by violating uniformity, when you get a clustering of numbers that violates uniformity. All right, so the other property, independence. This is two different die rolls, how they relate to each other. So two random numbers are independent if the probability of any random number for one of them is independent of the actual drawn random value for the other one. So one die roll cannot be predicted by any other die roll. A good example is this string of numbers where I see really no pattern. I see, I'm looking for repeats here. There's probably some repeats, but if I saw a number, it doesn't predict what the next number is going to be. 20 is followed by 4, is followed by 8. And I'm shocked I don't see any other numbers, but if I had another 20 in here, the next number that would follow after it would be anything. It could be anything. It's not necessarily going to be a 4. An example string that violates independence would be one where there's an obvious pattern. Like these numbers are sorted. 1 is always followed by 2, is always followed by 3. 20 is always followed by 1. So you end up getting this. So if you know if I don't know any of these, I would still say this has uniformity. This does not violate uniformity, but it does violate independence, because if I know more than one, I can see, I basically can get a pattern there. If I don't know any information, I don't know what this first one's going to be. It could be anything from 1 to 20. But once I know that the previous one was 2, then I know the next one's going to be equal 3. So even though it has uniformity, it does not have independence. All right, is that clear, the distinction there between uniformity and independence, how you can violate one but not the other? And these are questions also about midterm stuff. I love to give sample strings of numbers and ask you, does this look like it violates uniformity, independence, or neither? So those are types of questions that you might expect. Questions online? Okay. All right, so we now, so if we want to evaluate our random number generators, we need to be able to test for these two properties. So, so that's what we're going to be talking about here. So we're going to talk about how to generate the numbers and then how to test for these two properties. So any questions? Okay. So, so how do we generate random numbers? So in the physical world, we could do things that are very slow, like throwing dice, drawing from a deck of cards, drawing a ball from an urn. There are some things you can go online where people take images of lava lamps, and then they digitize the images, turning them into a bunch of numbers, and then generate a hash, which is kind of a special type of number out of it, and that ends up generating kind of a unique random number for every image here. So even though there's not a lot of difference from because the lava lamp moves so slowly, then there's still the small number of pixels generates a very different. There's a deterministic expression for this hash function that generates a very different number. So small differences in pixel position or color generate large differences in numbers, and so you can look at images like this, and this is a physical source of randomness. And so that's one way you could do it. If you go to random.org, which a lot of my empirical science folks go to, if they want to randomize the order of experiments and things like that, you can generate, very random, whatever that means, numbers, and it uses atmospheric noise as its source. And so it has sensors on temperature and pressure variations everywhere, and it takes all of those variations and it puts them together to generate strings of random numbers that then you can sample from here. So it doesn't use the methods we use. It actually is sampling from the physical world, and then it's taking that resource and it's making it available to you via a website. So those are other ways to generate these random numbers. But none of these are that practical for our simulations, where we want to run 1,000 replications of a simulation, and each simulation uses maybe 10,000 random draws of these random variables. And so that's a lot of numbers. So we need them to be generated quickly and easily. So our random number generator needs to have those properties. Those are required, but it is desired that they also be fast. It is desired that they don't repeat. Now, all random number generators inside a computer that are generated mathematically will repeat eventually, but we want them to repeat the sequence after millions of draws, so that when we're done with one replication of our sim, then the next replication is guaranteed to sort of get a different string of random numbers, and we don't start getting the same random numbers till way down the line. And by that point, maybe they'll be out of sync. And so still, it'll be a useful source of variation. And then the last property that we desire is that the random number have what we're going to call a seed. And that seed is sort of an initial number that starts the random number generator off. And every time we give it that same seed, it produces the same string of random numbers. So if we give it different seeds, we get different strings of random numbers. So within the seed, we get randomness, uniformity, and independence from draw to draw to draw. Across the seeds, we get independence in terms of you can't predict one sequence from the seed, a sequence from another seed. So it's like having 5 different 20-sided die, where this die produces the same string of numbers, this die produces the same string of numbers, and so on and so forth, but the strings of numbers across the die are very different. Now, why do you think it would be useful for me to have, and I also want this to be portable. So if I give my Mac computer a seed of 1, it'll generate the same string of numbers if I give this Windows machine a seed of 1. If I give a Linux machine a seed of 1, they'll all generate the same string. It's like we all agree that a seed of 1 is exactly this red 20-sided die. Why do you think it's important for us to have repeatability and portability? Any thoughts on that? This is one of the things that makes our experiments with computer simulations different than experiments in the real world. Well, there's a degree of freedom thing. I'm not quite sure quite where I'm going with it. So it's like I run a simulation and something interesting happens in that simulation. Now, if I ran an experiment in the real world, if something interesting happened in the real world, people will say, oh, did you get a videotape of it? Do you have that recorded somewhere? Do we have data for us to analyze that? And if you didn't, you're done. You just got to hope it happens again. But if we have this property, then what could we do if an interesting thing happens in our simulated world? Any thoughts? Well, how do we prove that it happened? By running it again. That's right. And so that's the cool thing about these computer simulations, is that every sim, somewhere in the sim, it stores along with the data from that replication, the seed for that replication. So if something unique happens, you can go back and reseed your simulation with the same number and then get the exact same output again. But now you can be sure to maybe probe the simulation a little bit differently. You could record more data. You can slow it down, zoom in on things. And so, and then on top of that, you can communicate a whole trajectory to someone just with one number. You can email your boss and say, I found a really interesting case. Can you run the simulation with seed 4,762? And let me know what you think. And if he runs just that number, he'll see a whole world unroll for him that's been indexed by a seed. So it's a way for us to index whole universes that we simulate, uniquely. So that's one of the things we do with a seed. So, so as an example, so one of the frustrating things about simulating in Excel is that seeds are chosen internally by the system clock. Every time you open up Excel, it needs a seed for its random number generators. And so instead of using a seed you provide, like Arena does, it just says, I'm going to use the second since January 1st, 1970, and that'll be my seed for my random number generator. Well, every time you open Excel or save a spreadsheet, that number changes. And so you get different random numbers out. So the exact same spreadsheet, if I look at it, save it at 126.29, and then I resave it at 128.06, and I look at the column there where I'm just generating random numbers, I get a totally different string of random numbers. So it's because in Microsoft Excel, it has a random number seed, which is inaccessible to you, unless you're using Visual Basic for applications or something like that. So this is one of the downsides of doing stochastic simulation in Microsoft Excel. You don't have repeatability. You can't just rerun a scenario. You have to, with its seed, you have to kind of hope you get that scenario spontaneously again, and then kind of grab the data the instant you get it. Now in Arena, it's different than that. In Arena, we'll see that there you can create, there's an elements template panel that has a seeds block, and you can pull in that seeds block, and you can actually change the seed for the default random number stream, which is 10. And so every time you start Arena, this starts with the default seed. Every second replication, they have a convention for how to choose that seed. So from replication to replication, there's always going to be different seeds. But every time you start Arena, it has the same exact seed, and you can change that seed, which you can't do in Excel. That's the reason why when you go into lab and you start running things, when you all build the exact same model and you all run them, you'll get the same outputs because we didn't have you change the seeds. So those same outputs, you say, wait, I thought this was supposed to be random, but I got a mean of 56.7 minutes, and my neighbor also got a mean of exactly 56.7 minutes. How could that be possible? Given this is supposed to be a random outcome. It is random, but you both kind of were instantiated with the exact same universe. And so you're just kind of like redundant copies of the same randomness. So if one of you were to go in and change your seed, then you would get different numbers out. All right, so there are questions about these ideas of seeds and so on. And the difference between Excel and the reason why you constantly get different random numbers in Arena, where every time you guys are going to run your sim models, you're going to get the same outputs unless you run a new replication. So you might run 10 replications and every replication will be different from itself. But across students, all 10 replications will have the same outputs if it's the same model, because they all start from the same seed. Okay. All right, so how do we generate these things? And I'll go through this kind of quickly here. There's a lot of historical ways to generate things. It doesn't matter too much that you know all the details here, but as kind of one random, so to speak, example, the so-called middle square method was an ancient way of doing this. And the idea would be you could start with a 4-digit seed, and you could take that seed and square it to give you an 8-digit number. And if it wasn't 8 digits, you'd pad it with zeros. And then you set the next seed for the next iteration to be the middle 4 digits. And then you square that. And then you keep doing that over and over again. And each iteration, the 4 digits that you pull out, you divide by 10,000, and that gives you your random number. And so that was one way to generate these things. The downside of that is that you would get a bunch of seeds that, based on the seed, you might degenerate to zero. So you get apparently random numbers that are kind of clumped a little bit, and then suddenly they hit zero. Then once they hit zero, you keep squaring them, you keep just getting zero over and over and over again. Or you get these things that repeat. And so you start with this seed, 6,500, you end up squaring it, you get a 2,500 seed, which in the end, after you go through this process, you keep getting that 2,500 seed over and over and over again. So you get this same number. And so you don't have uniformity there. So based on the seed, you get different streams that aren't really that great. And so, other examples here where you might start with a seed that looks like it's going well, but after you get past a critical point, then you get these tight repeats. And so you might think, oh, I generated 50 numbers and I didn't get any repeats. These look uniformly distributed, I must be good. But you have no idea that eventually you might burn out that transient and eventually get to this point where the same 5 numbers or the same 4 numbers keep repeating over and over and over again. So the middle square method has a bunch of these issues. It's cheap and easy to implement, but it's not really practical in the kind of desired terms that we talked about. So the more modern way we generate it, modern random number generators, you can pick any seed and you'll be confident that they're going to work. So that's a key point. Modern random number generators, all seeds for the random number generators will be uniform and independent. And so a random number generator that has this property, if you pick other parameters correctly, is the LCG, which you've had experience with on the last homework. So the linear congruential generator is a generator that has this sort of formula over here, where you pick these 4 parameters, the initial seed, a so-called multiplier, a modulus, and an increment. And the idea here is you take the previous seed, you multiply it by something, you shift it up by the increment, you take the modulus, and that then becomes the next seed. And every output is just that seed divided by the modulus. And so it's a pretty simple way to generate these things. There are variations where you can knock out the increment, and then it just becomes a multiplicative congruential generator. Or if you want to be clear that you didn't knock out that increment, then you can use this fancier name, the mixed congruential generator. But LCG is pretty much recognized here. And then there are, again, other variations that you can add to that, but this has some pretty good properties. The performance of this generator is very sensitive to these things, but if you can solve for the right ones of these, then you're really golden. And so there's old results, this Hole-Doble theorem, that if you choose a integer that divides m and c, so the only integer divides the modulus and the increment evenly is 1, and if the multiplier minus 1 is divisible by all prime factors of m, so you have to know all the prime factors of m, and then also if it's that multiplier minus 1 is divisible by 4 if m is divisible by 4. So it's weird that 4 pops up there. It's kind of like a weird leap year thing. But if those three properties hold, then regardless of what seed you choose, this LCG will have a full period, which means it will go through m numbers. So an LCG, the biggest period it could have before repeating is m, the modulus. And if these properties hold, you're guaranteed that it will actually go through the whole m period. And so it's pretty easy to set these things, and then you're free to choose your seed as you like. And so that's a really great property. So you've already done this on your homework, so I won't belabor this too much, but I start with a seed, you do the little formula, you get a number out. Whatever this number is, mod 100 gives you, so this number here is 502, mod 100. Well, if I divide this thing by 100, I get a remainder of 2. So I got a 2 out, 2 divided by 100.02. And then I just carry that on as you did on that homework. So the 2 replaces the 27, and then the 77 replaces the 2, and so on, LCG. And if I were to do that, then for this particular seed, I actually get a pretty long period, a period of 2,000 numbers. So that's not the full period, but it's pretty long. And if I take a histogram of all these numbers, it's uniform. So it has uniformity. I didn't do an independence test, but I'm going to claim for now that it has independence, so it looks good. The only downside of this thing is that it has a very short period of 2,000. And even if I got it up to 10,000, that's a very short period for simulations. I really need periods up into the millions or the billions for it to be useful for modern computer simulation. So behind the scenes in Arena, MATLAB, or whatever, a lot of them use a combined LCG, which just takes two LCGs and it sums them together and then takes that as the output. So this idea here, here's two. This is an example from a 1986 paper. This is one LCG implemented just like you did on the homework. This is another LCG just like you did on the homework. So different multipliers, no increment for these. These are just linear and or multiplicative, different modulus. And then if I subtract the two of them and take this modulus here, then I get a giant period, 2.3 times 10 to the 18th. So even though these have a relatively small period, the combination's got a gigantic period. And so that's really useful. And so if I were to take kind of a simplification of that example, here's an LCG I built that has a period of like 4, another LCG I built that has a period of 3. When you take the subtraction of those two, mod 3, even though the output numbers are only 0, 1, and 2, the period of the combined generator has got a period of 12, which kind of makes sense. It's kind of like the beat between these two. 4 times 3 gives me my 12. So combined LCGs give me much longer periods. So that's the thing that you should know is that LCGs have got all the properties we want, but they have short periods. Combined LCGs have all the properties of an LCG, but long periods. That's the takeaway that I want to make sure that you've got down there. And there are combined generators in the literature now that have even longer periods, like 2 to 191, like extremely long, to the point where you really don't ever have to worry about repeats. Okay. So questions about those properties: that an LCG's got uniformity and independence, a CLCG's got a long period as well, and those together end up making for a pretty darn good random number generator. And so the average random number generator is probably implemented inside Excel or MATLAB with a CLCG. There are cases where you have to choose even fancier random number generators for your simulations. We're not going to get into those so much. These are usually good enough for us, so we just kind of lean on the stock random number generators. But there are cases that you can find out there when you're doing sim for real, where you have to be much more careful about the random number generators you pick. So you just run sims, you know, it's really weird outcomes. And it turns out your weird outcomes are go away when you change to a different random number generator. So you end up finding these weird flaws in the random number generator. Any questions about that? Okay. All right, so let's wrap up with a uniformity test, and then we can talk about independence tests last time or next time. So we've talked about the ideal random number generator. We've talked about the crappy ways that kind of like that they started out, the modern ways of generating random numbers, and then now we need to know how do we gain confidence in our random number generators. So we need to talk about a couple of tests for uniformity for random number generators, and then what we'll talk about next time is a couple of tests for independence. So for uniformity, like I said, the output of a random number generator should be statistically indistinguishable from a uniform random variable distributed between 0 and 1. So we want to take a statistical approach, and so our null hypothesis is going to be that our random numbers are uniformly distributed. Our alternative hypothesis, which we would like to detect with the test if it's true, is that they're not uniformly distributed. So a good random number generator will not be able to be, you won't be able to detect the difference. Your p-value will be greater than 0.05, greater than 0.05. Now, a bad generator, which is the case we do want to detect, will be the one where your p-value is going to be less than 0.05, where we will want to detect the difference between these two. So the null hypothesis is the good result. Detecting a deviation from the null is the bad result. It indicates a bad generator. And so we're going to use a level of significance of 5%, which just means that the probability that our test will falsely reject a uniform generator. So how do we do that? Well, there's two methods that we talk about in this class. And the first one is, like I was saying before, we're going to cut up the interval into n subintervals and then see how many of our random outputs land in those subintervals. And we're going to compare the expected count to the actual count in each subinterval. And so whenever I hear the word count, so Count Dracula, count, my head as a statistician, as an industrial engineer, should immediately go to a particular statistical test, which is involved in testing counts. So whenever you hear count, you should think chi-squared. So the chi-squared test is a test for comparing observed counts with expected counts. So it's all about count. You cannot apply a chi-squared to any other type of data. It has to be count data. It has to be discrete data, count data. So that's count chi, those should kind of go together in your head. And so if, though, you have small sample sizes, you can't sort of count up enough for the chi-squared test to work. So if you have like a sample size of 5, you probably don't want to use the chi-squared test, and you'll use the other test that we talk about. So how does this work? So we would take a random number generator, or we would take an interval from a random number generator, and we choose a set of subintervals. And so I would tell you on an exam, like, cut it up into 5 subintervals. And so, then that ends up being your little n. So you're going to divide this thing up into 5 equal size subintervals. So 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, 0.8 to 1.0. 5 subintervals. Now, it's important that you cut up the hypothetical interval from 0 to 1. If I give you a bunch of random numbers on a midterm, they might be distributed from 0.05 to 0.97. And it's tempting to use that as my interval that I cut up into 5s. But you cut up the hypothetical interval, the null hypothesis interval. So you cut up the 0, 1. That's what you divide in 5ths or in 4ths. And then you count the number of samples that land in each bin. So once you count the number of samples that land in each bin, we're going to call that the observed number of samples for that bin. And there's an expected number of samples, which is just equal to the total number of samples divided by the number of intervals. If that total number of samples divided by the number of intervals is less than 5, you cannot use a chi-squared test. So that's the rule in this class. I think that's the rule that we use in 380 and 385. That's the rule most people out in science use. Yeah, if it's less than 5, if that's the expected count in each subinterval, you can't use the test. But as long as it's 5 or more, you can use the test. You count up every observed count, subtract off the expected count, square it, divide it by the expected count, and sum up all those together, and that's the so-called chi-squared statistic. And we then look in our tables to see how that statistic compares to what we'd expect under the null hypothesis. And you can think of the chi-squared as a measure of the distance from the null. The larger the chi-squared, the farther you are away from something that could have happened under the null. So we want chi-squared to be relatively small. Exactly how small we want depends on how many intervals we have chosen. So we will have to look up a critical value down here, this chi-squared, which is based on our level of significance, alpha, and 1 minus the level of subintervals. So if I have 5 subintervals, I'll look up the critical value for 0.05, 4. So you take 1 less subinterval. And after the midterm, we'll talk about where all of this comes from when we generalize the chi-squared test to other distributions. But for now, just think I need to know the level of significance and 1 less than the number of subintervals. So if I want to do an example of that, I'm testing these data for uniformity. I am told to cut this into 4 subintervals. So 0 to 0.25, 0.25 to 5, 0.5 to 0.75, 0.75 to 1. Cut all that up. I can count how many of these points land in each one of these subintervals. I see there's 3 that come into that interval, 4 in the second interval, 8 in the third interval, 15 in the fourth interval. Intuitively, I look at this and it's looking like things are going off the rails here. This does not look like it's uniformly distributed. In fact, I got 15 in one interval and 3 in another. So we want a rigorous way of doing that. So how many would we expect if it was uniform? Well, there's 30 points up here. 30 divided by 4 is 7.5. So I would expect each one of these to be close to 7.5. So then I'd say, well, how far away are each one of them? Well, I take each interval, 3 for the first interval, 4, 8, 15 for the fourth interval, subtract off the expected 7.5, square it, divide that by 7.5, add all that together, I get a number, 11.8667. I look up in my table and I say, I had 4 intervals, so I look in the third row of the table, and I want a 0.05 as my level of significance. My critical value is 7.81. Because this is bigger than that, then I'm saying this is way too different from what I'd expect under the null. So this is a bad random number generator. It violates uniformity. And so that's my conclusion. So I reject the hypothesis. All right, so that's an example of that one. We're going to do the chi-squared next time, as well as tested independence. So let me just jump ahead to the attendance question for today, and we'll pick up where we left off next time. So the question here is, what statistical test is associated with count data? And on the chat, I put that count in the big one. So when you see count data testing one distribution of counts against an expected distribution test, your head should associate the word count with this statistical test. So what test is it? Is it a t test? Is it a z test? Is it some other test? Which test is it? And otherwise, that's all I've got for you today. So we'll see you. Have a good weekend and see you next week. All right, any other questions online? If not, that's all we've got in the classroom here. All right, in that case, have a nice weekend. Hi.